Hello, everyone, and thank you for joining me. We're getting ready now to start session 2, and I'll go through and share the screen, which we normally do. Turn on the audio. Okay, now then, it looks like we're ready to get started again. And welcome back. Session 2, we're going to be looking at the solar power supply and all the well equipment that we're going to be using. There's going to be probably about 3 different systems, and I'm going to be breaking the next 3 videos up into the design of each of those systems. And like I said, we'll be moving to the actual lab upstairs, where I have a real nice board and nice cameras, where I can do a real pretty presentation for everyone. And so here again, this is the U.S.-India Water Pumping Partnership. It's the Hindustan Institute of Science and Technology and the Sri Ramakrishna College of Arts and Science and Alamo College District. Once again, my name is Craig Overmiller, and I'm the Program Director of Power Generation and Alternative Energy here at St. Philip's College, which is one of the 5 colleges, Alamo College District. And so in this PowerPoint, what we're going to be looking at is all the different equipment that we're going to be working with as we go through our installation in this particular course. And so we're going to start out with the solar power supply, because that's the first thing we got to build so that we have power on the site. The site is remote, and there is no electricity there. There is AC power, which I said in the first slide or the first session, but it's pretty far away, and we'd have to, I don't think we could run an extension cord that long. So let's just get started. So we're going to be looking at the equipment today, and this is going to be system 1, which is going to be the power supply. And this is where I had talked about. I'm going to show you something here in just a minute. This training will start with the solar power supply. In order to build our water pumping system, we need electric energy. We need power, both for construction and then to power the water well. And so we're going to have 2 forms of electricity. We're going to have AC, reason for the inverter, and then we're going to have DC. And so a lot of our equipment in the well equipment, most of the well equipment is all DC for this particular application. We do have an inverter so that we can have equipment for our power supplies. And so one of the things I want you to notice is, if you look right here where my cursor is, says 148. It should say 124. This is why I was talking about, it's real important when you order your equipment, and then when you get your equipment, make sure it's the equipment you ordered. Well, it came in, it was in a box, and the box said 124, which is 24 volt. But when we got around to start doing these sessions, we opened the box up, pulled out the inverter, and it was when I was making this particular video right now that I noticed that it said 148 and not 124. I went back and looked at the box said 124. But so what they did is they put the wrong inverter in the right box. So just, that's an important thing that you're going to have to look at. Make sure the equipment that you get is the equipment that you ordered. So basically, this is a pure sine wave inverter. It's made by Tokay company. I believe they're actually out of Canada. And it's a very nice inverter. It's 2,500 watts, goes up to 16 amps, continuous power, and it puts out 120 volts AC. But the important thing to remember is it says pure sine wave. If you want to try to turn a motor, you better have pure sine wave inverter. If you want to try to run a computer or anything where you don't want to see blips on the screen, you better make sure you have a pure sine wave inverter. All right, so the pure sine wave inverter, here again, the model number is an ST2500 148. We had ordered a 124. We now are in possession of a 124. The input voltage matches our solar panels. So you got to make sure you match up your solar panels. It really doesn't matter because we're going to be running through a energy storage system, also known as batteries. And so input voltage for this particular inverter is that the particular inverter that we have is going to be much less, and maximum 66 amps. And the output is going to be 120 volts AC. And when we're actually doing the install, I'll show you the proper inverter, and we'll go over the voltages at that time to make sure everything matches up, because it's real important that all these match up. In fact, when we go upstairs, we're going to be doing the math on the board so that you all know how to match up your equipment. It would not be pretty to put a 48 volt system on 24 volt, a 48 volt inverter on a 24 volt system. Low voltage is very dangerous, and it can harm your equipment. And so 2,500 watts continuous, and it's sine wave. So the purpose of the inverter is to convert DC voltage to AC voltage. And I know in India, I've been in India, and I was in Gujarat, and I know that your voltage is a lot different than we have here in the United States. We use 12240 mostly. A lot of times we have 480 volts, 480, 277, and that's on a commercial. And then we also have another commercial voltage, which is 208. And all of those commercial voltages are all three-phase. Residential is what we call single phase. And if I'm correct, I think when I was in India, most everything was 440, three-phase power. At least it was on the campus I was staying at in Gujarat. And be sure it's a sine wave inverter, all right? They are very easy, much easier on the motors. Sine waves are pure sine waves. They're not square waves. Square waves, pure sine wave makes the motor turn easier. And so what we have right now is 48 volt DC inverter, but it's supposed to be 24 volts because all our system is 24 volts. And I'll get everything corrected. I wrote this according to what we should have had, what we got instead of what we should have had. So the inverter should have been an ST2500 124. We will be using this one when we set up a prop until the correct one arrives. Well, the correct one has arrived, so now we're in good shape. And this is why I say check your inventory. The vendor sent us a 48 volt instead of a 24 volt. Then we requested a replacement, and they were very, very good because they knew the urgency for this particular joint venture that we're doing together. So these are the solar panels. We got 2 solar panels. Very nice. They're 140 watts each. They're made by Solarland. And actually, this is a product of Vietnam, which is interesting. Vietnam's really coming along and being another good partner for the United States now. It's a Solarland 140-24, so that means they're 24 volts, 140 watts. Volts open circuit. Whenever you're doing designs, a lot of times you want to look at what the open circuit voltage is, because that's usually the number you use when you're doing the design, is 43.97. Even though it says 43.97, the nominal voltage of these solar panels is 24 volts. And so you want to use it on a 40 volt system. If it was a 48 volt panel, it'd be up in the 54 range. The short circuit current, ISC, that stands for short circuit current, is 4.02 amps. That's the other number we use for design. And then the VMP. So once the pump and the batteries and everything actually connects to the solar panel, the output is going to drop down to a connected voltage. And so the connected voltage is 36.95 volts, and the connected amps maximum power, MP. You'll hear maximum power a lot as we go through water wells because we use maximum power point tracking, MMPT, is what makes water wells work through the controller. And so IMP is 3.79 amps. And so this is called the label on the back of the solar panel. So you have the front of the solar panels. And as you can see, you can actually come in and count the number of cells. I believe this is a 72 cell module. Let me count real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 times 4. I might be wrong on that one. I'm using my calculator on my cell phone. 72. Actually, I'm right. Okay, so 18 times 4 is 72. It also tells you your class and your groups. It gives you all the different things that you need to know. And it also gives you all of your, what am I trying to say? All your different listings, you know, that this thing is rated at. And 1703, which is very important here in the United States, as a classification for a solar module going through its different testing. And so you can see right there on the back of the label, it's got the CE, it's got the SA, it's got the ISO, it's got all the different classifications and certifications required through most of the governments throughout the world. Now then, when we come off the solar panels, the first thing we're going to do is we're going to hit a charge controller. We're going to use 2 charge controllers. I think we can get by with 1 just because of the amperage that these can have. Let me go back up. The solar panel is going to be putting out, for our design current, it's going to be putting out 4.02 amps, okay? That's your short circuit, that's your design that you use. So we can just go back over here. So 2 times that is 8.04, and these things are good for 10 amps. So we could actually put 2 solar panels in series and then connect them, no, in parallel, I'm sorry, in parallel, and then connect them to one of these charge controllers. To be on the safe side, I think we're going to just use 1 charge controller for each module and connect them up. This charge controller, what it does, the charge controller goes between the solar panel and the battery. And so the charge controller's job is to protect the battery from overcharging from the solar panel. And then also, sometimes solar panels don't have what's called a blocking diode in them, or and so what happens is at nighttime, the solar panel becomes a hot plate and discharges the battery as heat through the solar panel. And so that's what's nice about this charge controller also is it has a load controller, which is located right here. Now that load controller, what it does, it disconnects the load if the battery voltage gets below a certain set point, so it does not damage the batteries. Its whole purpose is to protect the batteries. We may or may not use that. I don't think it'll be a bad thing to do, and it can handle up to 10 amps. Most of our pumps are right at 8 amps, I believe, and so we just got to look at that. We could probably use. We have 2 different pumps that we're going to be using. So we can put 1 pump on 1 charge controller on the load control and another pump on the other charge controller, load control. That'll help us quite a bit. So the nominal DC voltage coming into these charge controllers, 24 volts. Minimum solar array voltage is 30 volts. Maximum solar array voltage is 60 volts. We're well within that spec using, if you go back and look at those modules. Maximum solar current is 10 amps. Maximum load current is 10 amps. I think we'll be good on both of those. We'll just have to look as we go through. We'll check again as we go to hook these up, just to make sure that we're within spec. We don't want to hurt any of our equipment. And one of the things too is these are not polarity protected. So these particular charge controllers, some charge controllers are. What that means, if you accidentally hook the negative up or switch the negative and positive, you just lost a charge controller. You're gonna have to go buy a new one. These are not forgivable at all. You make one mistake on these charge controllers and you're gonna lose your charge controller. Now then, this is kind of the data sheet on the charge controller. And I highlighted our different areas of the charge controller we're using in yellow. And those items specific to our controller are highlighted in yellow. Since our pumping system is 24 volts DC, we're using a 24 volt controller. This controller can handle up to 60 volts and 10 amps on the input side. We will be placing one controller per module, which I said previously. Or we could do two modules in parallel to one controller, because it's still well within specs. So if you look at the different specs, we have the model number, and it shows us our solar current, which is 10 amps, our load current, which is 10 amps, our system voltage, which is 24 volts. And does it have a low voltage disconnect? Yes, it does. So regulation on our voltage. So we're at 24 volts. And so we have a sealed battery, so we can go to 28.2. And our low voltage disconnect is going to disconnect at 25.2 volts. Our 24 volt battery, maximum input is 60. We should be good there. Load in rush capacity in amps is 65 amps. I don't think that's going to be an issue. Sometimes, when the temperature really drops, it's a really nice, bright, sunny day, and it's, 32 degrees Fahrenheit. Your amps are going to spike way, way up. But it shows you where your different input, if you look at the picture, you got the solar panel, you have your batteries, and you have your load. And so it's pretty easy. That little symbol right there on the battery coming out of the charge controller going to the battery, that's a fuse. We actually will probably be using some safety disconnects, which aren't in the picture. We'll show them when we do our design, where we're going to be putting our safety disconnects to protect us and our equipment. And also the safety disconnects allow for us to do maintenance on different components of the system without having to take the whole system apart. These are the batteries that we're going to be using. Crown is the largest battery manufacturer in the United States. There's only two manufacturers. There's Penn and Crown in the United States. And all the other batteries are that particular battery, and they have all Penn or Crown has done is put that battery label on it. So Walmart has a battery, Academy has a battery, and they're all from one of these two companies. They just have their own proprietary labels put on those batteries. For our solution, I've chosen a commercial deep cycle battery. It's going to be very good. It'll last 5 to 8 years. The battery has 130 amps at a 20-hour rate, which means if you divide 130 by 20 hours, you can put a load of 6.2 amps on that battery for 20 hours, okay? And that's important because the sun comes up every 14 hours on the worst given day, which is December 21st. So you have 14 hours of darkness on December 21st. And so if you had to run a full load of 6.2 amps, which is what this battery is telling you can do. Now, if you need more than 6.2 hours, you just put more batteries in parallel. And And so that's how you get around that. We'll talk about that more too when we're up on, and we're doing designing. Um, and so our surface pump pulls 8 amps. And so, and our water well, I can't remember exactly. We'll see here in just a minute how many amps it pulls. Um, and so you take 130 and divide it by 8 amps. So you could actually run it for 16.25 hours. That's still within that 14-hour window. So that's where it's really important whenever you're figuring out your 20-hour rate. You know, you divide it, you know, your battery reserve amps by 20 tells you your maximum load. Well, not your maximum load, but you know how they get their number. And so then you take your actual load and divide it into 130. As long as it's more than 14 hours, you're in good shape. Okay. So, or less, you know, whatever, you know what I mean? You got to have more than 14 hours of reserve capacity because the sun's coming up every 14 hours. In order to get 24 volts from the batteries, we will place two 12 volts in series. The volts will increase to 24 volts DC nominal. They're actually going to be around 13 and a half. So that's 20, 23, 24, 26, almost 27 volts is what you're actually going to have. You know, we'll put a voltmeter on it when we're out on the job site and doing the install. We'll take a look and see what it actually pulls. And let me get my pretty face out of the way again. So the voltage will increase to 24 volts DC nominal, but the amps will remain at 130. So when you put batteries in series, you're increasing the voltage, right? But you're not changing the amps at all. So our voltage is going to be a nominal 24 volts, but our amperage is still going to stay at 130. And we'll go over that more and more when we go upstairs and playing on the big board and doing our designs. So this gives us a 24 volt DC nominal rating, 130 amp battery bank. Series builds volts, parallel builds amps. And if you look right here, I have the battery spec sheet. It's a 12 volt deep cycle commercial battery. It's a, I can't remember, the numbers are kind of hard to see. It's a 130 on the 20-hour rate. And it gives you different specs, tells you how much it weighs and things like that. It gives you the size of the battery. I think the weight is 66 pounds. And so it's a good chunky battery. Now we have, oops, sorry. Now we have the racking system for the solar modules. And so on this one, I chose a pole mount system. Pole mounts, they stay cool. They keep your solar panels cooler than any other mounting system. The cooler the solar panel, the better it works. Heat is your enemy when it comes to solar. The hotter the solar panel gets, the less efficient it is. And so it will actually put out less power. The pole mount racking system is designed for 2 of the PV modules that have been purchased. It's a simple, easy tilt assembly. All I got to do is pick up a 2-inch, which is a 2-inch galvanized pipe, which is a 500 millimeter by 10 feet long. And then we're going to take that, we're going to get 2 bags of concrete, 2 bags of cement, and we're going to go dig a hole, and we're going to put that pipe in the hole, and then we're going to build this racking system. And then we're going to mount the 2 solar panels to the racking system. And I like just going ahead and mounting the charge controllers to the back of the modules so that we keep everything nice and short on the wire runs. And when we go to install it, this has 2 directional tilt. So you can change the azimuth, you know, on your compass. And so you can turn it to north or south. And I mean, you know what I'm saying? You can change it to due south, southwest, wherever you're going to get the most sunlight during the day. And then you also can adjust the tilt for your latitude. Now then, this brings us to our pump. And this is going to be the one that we're going to use for our well. It's made by Sun Pumps. They're in Safford, Arizona. I've actually been there. Actually went to their plant. I wanted to go see what they built. So the model is an SDS Q128. And the maximum flow is just small, but we're using a storage tank. So we really don't care. We're just going to fill 1.3 gallons per minute, you know. So we're going to have well over 60 gallons every hour. And if you just figure, let me get my calculator again. So if we take 60 times 5, so we're going to have 300 gallons a day minimum. Our storage tank is 500. I bet we'll fill that in one day without any trouble, because we're using a pump controller. And the pump controller job, I mentioned before, maximum power point tracking. So maximum power point tracking turns high amps into voltage. The pump wants volts. And so when the sun comes up, you're going to have your watts is constant on the solar panels. You got 140 watts on each, but the voltage is going to be low, so the amps are going to be high. And so what happens, it knows that there's 140 watts, and so what it's going to do, it's going to lower the amperage and increase the voltage, and that's called maximum power point tracking. So this is going to give us 4.7 liters per minute. Maximum head on this one. Head is how far down it can go in the well. And so it can go down 230 feet, which is 70 meters. Maximum power for this guy is 123 watts. We don't really care because the pump controller is going to take care of that for us. We have two 140 watt modules. All right. Now then, don't say anything. I don't look at, I'm trying to figure out what our amps are on this guy. We'll figure it out here in a little bit. Once 123 watts at 24 volts. So that should tell us. So we take 123, I'll get my calculator again, 123 divided by 24, 5.1 amps is what this guy is going to be pulling. Well within our charge controller load control. So we're in good shape. This is a small pump just for training purposes, for the purpose of these sessions we're putting together in this training. I'm going to show you much larger pumps when we get in the field. Like I said, I've got pumps that go down to 1,200 feet and will pump 10 gallons per minute at 1,200 feet. Larger pumps, like I said, will be on the side for comparison. The pump will require a controller. Most pumps do require a controller, and you want that controller. Make sure when you order your pumps or install your pumps, check to see if they require a controller. Most of them do. Now, the one I say that, but the one I have a demonstration one that's already been built, and it does not require a controller. So it just requires power. So this is the pump controller, and this is what we're going to be using to make sure our pump is running and is always in good shape. And also another thing the pump controller can check, if all of a sudden your pump is above the water level, it turns off, which is nice. The purpose of the pump controller is to protect the pump. It ensures the proper voltage and amps to the submersible pump for optimal performance. It acts like a multiple power point tracking device, changing the volts and amps from the panels or the batteries to increase the water output. The controller can take power directly from the solar panels or from the batteries. We will experiment with both, and then we're going to just try to figure out which one gives us the most water, because the whole idea is to get the most water. The batteries will be needed for additional DC and AC loads, because we're going to also hook the inverter up to the batteries. So we'll be running our AC loads off of the batteries, and then some of our DC loads as well. We will be installing a transfer switch for easily changing from solar panels to batteries. And the next slide shows the wiring of the controller. And then via a float switch, the controller tells the pump when to add more water to the storage tank. So our float switch will be coming in here in a little bit, and we'll see how it gets wired up as well. And we'll go over it real well when we actually are doing hands-on in the field and looking at how all this actually goes together. This is a good option to have the float switch. It reduces the runtime of the pump. So the wear and tear on the pump is greatly reduced, which is always a good thing. You got to protect those pumps. Those pumps, they only last, a couple of years because of wear and tear. Mainly silt gets into them and tears them up. And so you want to make sure they're only running when they need to. Okay. So here's the wiring diagram on the pump controller. There's that safety switch I talked about. I'll show you here in a second. In this diagram, the red conductors are positive and the black conductors are negative. The green conductors are our grounds. And now grounds are very, very important, and they may save your life. This is a 3-wire pump system, very simple hookup and installation. Now then, this is the DC disconnect that I had told you about, the safety disconnect. We're going to put that in there. We don't need one on the pump. We probably don't want one on the pump. We want the controller just to have full access. We'll also have, instead of the DC switch right here, this will probably have a transfer switch, so it can take electricity from the solar panels, or if we had a battery bank sitting right here, it could take it from the battery bank. And so you can see how the solar comes into the disconnect switch, and then the disconnect switch comes over and goes up to the controller. And so you have the PV negative, PV positive, and then you have your pump positive, your pump negative, and of course your ground. Now then it only takes microvolts to if it goes across your heart to stop your heart. So you want to make sure everything's grounded, because you do not want to be the ground. Okay, so now then, this is my favorite thing. I do lots of wells here in Texas, and especially on the ranch we're going to. Well pipe or tubing, I use tubing, and drop cable. So what I like about tubing, it's continuous. It's one continuous piece. It's the full length. And you can just lower it down the well almost like a hose. It's pretty stiff. Leave it in the sun, it helps it to loosen up a little bit. Well pipe comes in 3 different types: PVC threaded, metal threaded, or my favorite, which is this, is poly tubing. There are advantages and disadvantages to each. PVC and metal come in 10 or 20-foot sticks, what we call them, 20-foot lengths. The tubing is continuous, which is what I like. There's no joints. Plus, you can, if you have a big wheel, and I'll show you, we'll use the wheel when we go out to do the install, you lower the tubing using a pulley. And it's a very nice system. It makes it very easy. It reduces the weight of the pump. The further down the pump goes down that well, the heavier it gets. And so don't ask me why. I'm not a physicist, but it'll get to a point, a well pump that only weighs 40 pounds, by the time it gets down to 200 feet, it's going to be in the 300-pound range, and it's going to be hard to even hold on to it. But this makes it very easy. All right. So we'll be using the tubing for this install, but I'm going to show you the PVC, and I'm going to show you the metal piping that goes with it. We also have a drop cable, which we'll demonstrate on site. The drop cable basically is just in case something happens, like your pipe breaks, PVC pipe breaks, the tubing pipe breaks, the fittings get pulled apart. The drop cable is basically a safety device, which will keep the pump from dropping to the bottom of the well, and then you're going to have to go and try to get it. These pumps are made out of stainless steel and brass. You're not going to be able to use a magnet to go find it. A lot of people, I'll just drop a magnet down there. No, you won't. At least not with this pump. Some pumps are made out of steel, and you can drop one of those big, heavy duty magnets down there and snag it and pull it back up. I've been lucky a few times. I've had stainless steel pumps fall down a well, but I just dropped basically a ship anchor down in there, a little small ship anchor, and managed to tangle the wires and pull the pump back up. I just got lucky. So the drop cable, I do it. Just it'll make your life easier, if something does go wrong. Now then, we have casing and the casing cap. So the purpose of the well casing is to protect the sides of the well and prevent collapse. It protects the quality of the water from sediment. It provides a channel for easy maintenance and repair. Casing does not need to extend the full length of the well, but it's a good procedure to follow. The bottom 10 to 20 feet of the casing should be perforated casing, and it has a screen around the outside, perforated screen. And the purpose of this the screen is to keep the sediment out, but it's to allow for sufficient recharge from the well. This is very important. The well needs to recharge faster than you're pumping water out. And so you need to know what your recharge rate of your well is. And sometimes you can find it. The government has that documentation for you, or you just pump your water until it runs dry, and then you know what your recharge rate is. And so you may have to just experiment with that on your own with your water well. Your water resource needs to be positive, okay? So you gotta have more water coming in than water going out. The above picture that we're looking at right now is of a well cap and the well cap attachments. So these are all good things to have. The cap has many functions. It is where vertical pumping becomes horizontal pumping. And so this is where your PVC pipe or your tubing or metallic pipe, whatever you choose to use, this is where it comes to the surface. And this is where all your connections go. This is also where the vertical pumping becomes horizontal pumping, where water penetrates the surface. It supports the well piping. It secures the drop cable or safety cable. It allows the electrical power to reach the submersible pump. This is going to be the access. And this right here is going to be that little fitting where the electrical conductors go through. And you want to make sure you have this is made out of steel. And so you want to make sure that your electrical wiring does not come in contact with that steel. And so this is an insulated connector that allows for that to happen. These are also stainless steel tubing connectors, so that we can connect our tubing and then connect our tubing to this device. And these can get pretty fancy, and I'll show you some of the things that I do when I'm on the job site. It also has these bolts where you can connect a handle to it, so you can easily grab onto it and pull it up. And I like hooks because, like I said, when you go to pull this thing up, by the time you combine that tubing and the pump, you're going to be 300 or 400 pounds. And so you're going to need something that's going to be able to lift that up. I know I can't lift 300 or 400 pounds. System 3. Okay, so this is our water storage and purification system. I'll let you see right here that it does say systems, okay? And this is the ABS storage tank that I talked about. This is a 500-gallon tank, and it's used for water storage. And we even got a little bottle right there. So that's another form of water storage, that little water bottle right there in the background. There's a huge benefit to water storage. It gives you a reservoir of water in time of drought. It gives you a reservoir of water if the pump goes offline, or if you have to take the pump offline during maintenance. It also, it's just nice to have a good buffer. 500 gallons is small. The system that I've already have installed that we will look at, it's got a 3,000 gallon tank. And so I'm not sure what that is in liters, but you all probably know that just off the top of your head. Also, what it allows you to do is build water pressure. And if you elevate this tank to, let's say, 15 feet above the ground, and we'll actually do the calculation to see what that pressure is, because we use a lot of 2-inch and 1-inch pipe when we do water. Actually, 1.5 to 1.25 to 1 inch are the size piping that we use. We use PVC for our horizontal piping and for our plumbing network that we're going to be building. We'll calculate what kind of pressure you can get out of 500 gallons at 15 feet. You'd be amazed. It's going to be a lot of pressure. And we'll do that when we're up on the board and when we're doing this particular system. Another thing too is it allows you purification, okay? You can drop ozone, an ozone system in here, a UV system, and a chemical system, all inside this tank, and purify the water to where it's potable water, where it's drinking water. And then also I like to take it through other filters, especially if you're using chlorine. I like to take it through some charcoal filters and chlorine filters that remove the chlorine taste. Doesn't remove the chlorine, but it removes the taste, plus it makes the water look very, very clear, okay? So if you do raise it 15 feet up, you have to add that additional 15 feet to the height of your pump. So our pump is good at 230 feet. We'll probably have the pump sitting at around actually 180, somewhere in that area. And so we're pretty good, you know, even with 15 feet additional, we would be good if we, you know, put the tank up in the air to get pressure. We're not going to do that. We're going to be using a mechanical system. And so that's what we have. So I'm going to go on to the next one. So now then, I want to move my picture again. This one's pretty important. This is the float switch. And when you have water storage, this float switch actually hangs from the top of the tank. It's got a weight on it, and it's got a float on it. And so you can control how many gallons you want in that tank. I'm going to want the full 500. And so you put the float switch in there, and you can see how it works. The weight holds the float switch down into the tank, and when the float switch floats up and the top of the switch is totally in the up position, it turns the pump off. If the float switch is in any direction other than straight up, the pump will come on if it's in any direction but straight up. And so this is what's really nice of turning the pump on and off and maintaining your reservoir of water that you're going to want. So with the pump controller comes a float switch that monitors the water level in the storage tank. This is a great feature. The float switch monitors the level of the water in the tank and tells the pump to turn on and replenish when needed. This reduces runtime in the pump and saves on maintenance and downtime. It also gives the ozone and time to work, and the chemicals time to work. So, and this is how it's got a special in the controller. It's got just 2 wires. It's actually just a contact, right? So all it's doing is coming down, making a contact. It closes the switch and energizes the pump. That's all it does. Pretty easy. Okay, now then, we're into water purification. So we're going to be looking at two systems. The other system is already at the site, so you're not going to see it in this particular slide. In the United States, drinking water is treated chemically with chlorine, ozonation, and UV light. Ozone is concentrating the water with oxygen atoms. No known bacteria can survive in ozonated water. UV light needs to be in the 280 nanohertz range to purify water. This ozone system right here, and this one right here inside where it says O in this gray box, it actually has a UV light in there, and what it's doing, it has a pump on it, and it pumps air into the water, much like, you know, you pump air into a fish tank. And so, but it's not pumping air. It's taking the air, sucking air in, it's frying the air with UV, and then it's turning the air into ozone. And so what's the one thing that we have a problem with? This is actually pretty good for the environment too, because you always hear about how there's a hole in the ozone. Well, this type of water purification adds ozone to the atmosphere, so it closes those holes. So this is the good ozone, okay? It's not like the fluorocarbons that eat holes in the ozone. So this ozone kit, manufactured by O, you get it, 3 oxygens. You need a certain amount of ozone per gallons of water. This particular system is good up to 3,000 gallons. We have 500 gallons, so I think we're covered pretty well with that. You know, we're overkill of 6 times. The system requires AC power, and so we'll use our inverter to run this part of our system. And the UV system we will build ourselves in the lab, and then we're going to install it in the field. So you'll actually see building the UV kit. The UV kit has to be made completely out of stainless steel. And it's got to be, I forget which one it is, it's like 340 or something like that, stainless. And it has to be a particular type of UV bulb. It's amazing. I made one of these systems out of ABS black plastic, Schedule 80 PVC, basically. After 2 years, the UV literally ate holes through the PVC, Schedule 80 PVC, which is pretty thick. And but if you use stainless steel, you won't have that problem. Plus, you have to use a sealant called butyl, because they're all, both the stainless steel and the UV is, and stainless steel and the butyl are UV resistant, you know, so they say that's the best you can use for that. And so I think this might be our last slide because it's the water for purification. And if it is, nope, I take it back. System 3. We still got to pressurize this thing. So we talk about pressurizing by putting your pump in the air, which is quickest, probably the simplest and easiest way to pressurize your water. Gravity is great, water is very heavy. And when you put 3,000 gallons in the air and you try to press 3,000 gallons at 15 feet through a 1-inch pipe, you're going to get a lot of pressure. And so horizontal pumping is what we're going to look at. Now that the water well is stored and sanitized, we need to think about horizontal pumping and community water. So some of our water is just going to go to open tanks, you know, for the livestock. But some of it we want to go to us. You know, I'm thirsty. And so it's stored, it's sanitized, and now we got our community system. So we come out of the storage tank and go straight to a charcoal filter. From that filter, we go to our pressure pump. Pressure pump is pictured right here, and you can see all the good stuff on it. This is a mean pressure pump. It can move some water. And for as small as it is, it'll do very well for our training that we have here. So we come out of the storage tank, go to our charcoal filter, and filter, we go to the pressure pump. The pump shown will achieve 60 PSI at 24 volts. And so it's going to use 8 amps. Most domestic water systems are 40 to 75 PSI. The system that I've built for that we'll be seeing as a parallel system that's already been built, it's set at 50 PSI. The system needs to maintain that pressure. In order to do this, we add a pressure tank. The blue pressure tank will have a water reserve capacity and can maintain water. I think this one has a capacity of about 50 gallons. You know, pressure tanks, you know, they're huge. They can be thousands of gallons. They don't, you know, we're just building a small little system here just to show you how it all is done, and can maintain a pressure up to 150 PSI. In the field application, we'll build a manifold that will allow the piping to go in different directions. It's best for protection that the piping be underground. And our next session will be in the lab designing our entire water pumping system. So maybe this is our last slide. Just going by what that just said. So this is system 3, and I think this is all our different systems. I don't think there's anything left. And so, yep, that is where we're at. So I am going to say stop share. And now we're back into the lab and or the classroom. We'll be in the lab tomorrow. And so hope you got a lot out of, you know, the different equipment we're going to use and understand more, you know, when we actually go to put all this together, you'll be able to see. And when we actually do put it together, you get to put your hands on it and use the different tools. I'll be doing it for you actually. And, but you'll be able to follow along and see how everything goes together. And we'll even talk about the different conductor sizes and things like that for our different wires as we're putting all this together. So hope you all had a good day. And I'm going to end this particular session, and we'll see you for session 3 in the lab upstairs. And when we get up there, we're going to start, actually, we're going to take each system and design them one at a time and draw them out. And then once that's done and we have our design, I'll take pictures, and those pictures will wind up being our blueprints. And then when we go out into the field, those will be that's how we're going to assemble this project. All right, y'all have a good one. See you at the next session.